All right, it's an honor to be here, and thank you for the intro, and thank you, Ed, just for the presentation. So this talk doesn't have a lot to do with TiDB and HTAP. It more has to do with sort of our vision of the future on the analytics side, but I think some of the lessons we have learned can actually be applied to the transactional side as well. But just in case you're wondering, hey, did I walk into the wrong conference? We do love TiDB at Databricks. We use TiDB quite a bit, powering some of our most important infrastructures. But let's get started with this talk. So the whole field of relational databases really started, I think, almost 50 years ago at that point when Ed Cott published, am I blocking you? Ed Cott published a seminal paper, which actually won him a Turing Award. And the paper's title is A Relational Model of Data for Large Shared Data Banks. As you can see, at the time, the term databases weren't even commonly used. He used the term data banks. The most important sentence of the entire paper, in my mind, is actually the very first sentence in the abstract. It just states, future users of large data banks must be protected from having to know how the data is organized in the machine. All right, it's stated in 1970. Now, I just want to get a show of hands. Please put up your hand if you ever had to, either if you use the analytics system, partition the data set, or cluster a column, or add an index to a table to speed up your queries. All right, virtually everybody. I mean, if you haven't, you probably haven't actually used anything for real. Now, can you also put up your hand if that very optimization you've done slow down your queries, so accomplish the opposite effect, or accomplish the opposite effect from some other queries that you're trying to do? All right, it's about maybe half of the people put up your hand, or surprise you in cost. All right, so the now, what's going on? How can sort of all these optimizations that you're doing actually slow down, or accomplish the opposite effect? Let's just look at a very, very simple query. By the way, this talk has varying degree of technical difficulties. It's not going to be too complicated. I'll show you a little bit of math, but it's not that hard. And for some of you, it might feel it's too easy, but just bear with me. All right. So very simple query. Just like start from events where user ID equal 1, 2, 3. Everybody would know how to optimize. If you want to speed it up, you just create. You don't want to be doing full table scans every time. So on the analytics system, most likely you would start by, hey, let me partition by this column called user ID. Now, but let's say you have other queries that your users run. For example, sometimes they filter by the event ID instead of user ID. So people add, hey, maybe add an index, or I add a cluster by in the analytics system called event ID. The problem with all of this optimization is that they actually introduce what we call write amplification, which means for every record you write at this point, you would have to write to multiple locations because of the clustering or the partitioning or the indexing. And sometimes it's a straightforward write amplification. It maybe reduces your write throughput by 2x or 3x, depending on how many indexes you add. But sometimes, in the case of a partitioning, for example, a single record insert could actually trigger a massive amount of compute in the so under the hood, which creates very unexpected results. So in summary, just with a very, very simple example I show you, my interpretation of Cott's talk is, hey, systems should be super easy to use. I never have to worry about how data is organized. I never have to think about optimization. I just specify declaratively what I want with queries, SQL queries, and I get results back. And they should be fast, as cheap as possible, and super easy to use, right? But in practice, that's never true with any databases, including Databricks, including TiDB. We have to choose 2 out of 3. Sometimes you choose only 1 out of 3, all right? And all of these trade-offs become knobs you have to tune the systems. That's why the job of DBA exists. That's why engineering spend massive amount of time trying to optimize data systems. Now, let's just maybe study a little bit more under the hood what's happening with database systems. Here's how most databases at a 20,000 feet level, how they sort of execute queries. In a sort of traditional database system, you generate your queries in SQL. In a lot of the more modern analytic systems, you can generate sort of your queries in different programming languages as well. And you get this query plan, and you pass the query plan basically specifies declaratively what the queries want the results to be, but It doesn't actually specify how to execute it. And there's this thing called a query optimizer that determines, hey, how should the database system actually execute those queries? And there's this little thing that's fairly important called a cost model, which is basically an R code that tells you how expensive a particular way of executing a query would be. And the optimizer consults the cost model and picks a query plan to execute, and it executes it. Right? It's a very high level. Now, the very classic, I'm showing you a lot of papers here today. The very paper that laid down the foundation of query optimization is access path selection, published by Pat Sullinger from IBM Research, almost, I think, probably like 30, 40 years ago. In this paper, it laid down how you can, how cost model should work. All right, so going back to our example, select star from events where user ID equal 1 to 3. The cost model from the Sullinger paper effectively says, hey, the cost of this query will be roughly 1 divided by the cardinality of user ID. So if you have 100 million users, you have 1 divided by 100 million times whatever size of the table you have, right? Now, some of you might ask, but does this even make sense? Are all users the same? Let's say if this is Twitter, and you have Elon Musk as the user. Elon Musk must generate way more events than maybe some random other person that nobody's following, right? The reason is, well, the cost model is very naive and it assumes uniform distribution because it doesn't actually know what's going on with your data. Now, some of you might ask, hey, but that was like a paper published in the 70s or 80s. There must be a lot of improvements. In some sense, you're right. In the last 40 years, there's a lot of papers published. There's sort of thousands of them. Here are some of the more important ones. You can see like people come up with interesting ways of, like for example, bushy trees, snowstorms. Hey, how do I deal with maybe independence? How do I deal with correlation? All of those things. But at the end of the day, they are not that different from the very simple model. They just try to add more and more heuristics to deal with some of the cases we've seen that have happened in reality. So I think about maybe 5 years ago, there's this paper published by the team from TU Munich. Actually, we just met Victor yesterday. And in this paper, they try to study, out of all the commercial and open source databases, how good are their optimizers? How often can they generate the right plans, and how wrong are they usually? Now, there's a lot of data in this paper. I encourage you to go check it out. It's actually surprisingly bad, all the optimizers. And there's one, the money chart is this one. It basically says, hey, 25% of the estimates can be 6 orders of magnitude wrong in a query optimizer, all right? So if you make a mistake, the 6 orders of magnitude wrong in your job, you'll be fired. But when a database makes a mistake, the 6 orders of magnitude wrong, you have to learn how to deal with it. So 50 years of relational database research is somewhat of a pathetic moment that basically we haven't realized cost vision. Trade-offs in performance and cost are basically leaky abstractions. Despite all the optimization, those become knobs, and they're very, very difficult to tune. And the fundamental reason is all the system architected with tons of heuristics that basically fall apart in real-world scenarios, because those are heuristics some engineers came up with without actually understanding or having access to the actual workloads. So one thing, a few years ago, so us and a bunch of other ideas had this idea of, hey, but does this seem like the perfect AI problems? In a lot of AI systems you have seen in the last maybe 2 or 3 decades, a lot of AI programs went from heuristics-based if statements to sort of learning from real-world data, right, and come up with machine learning models. This doesn't seem that different. As a matter of fact, it has a lot going for it from an AI perspective. It's plausible. Like mankind have run a lot of real-world queries in the past. And this complex workloads are difficult to model by heuristics. And last but not least, the workloads tend not to change dramatically, like in a matter of seconds. They tend to change slowly, and slow here. It could be like minutes, they tend to change slowly. And as a result, it gives the opportunity for AI to learn and figure out what's going on. Now, we're not the very first sort of set of people on the planet to come up with this idea. As a matter of fact, Google, there was a paper from Google in 2018, collaborating between Google and MIT that came up with this paper called The Case for Learned Index Structures, in which is that we posit all existing index structures can be replaced with other types of models, including deep learning models. One of the authors of the paper actually joined Databricks shortly after the paper was published. But there's an interesting thing, which is, but this paper was pretty groundbreaking, it's highly cited, inspired a lot of sort of work in this area in academic community. The problem is we have never actually seen this working in practice. And trying to figure out why. And it wasn't just Google. For example, our friends at Berkeley, actually my co-advisor, Jan, wrote the paper called Deep Unsupervised Cardinality Estimation. One thing, I actually worked with them very early on this paper, and I basically showed them the optimizer paper I just showed you earlier and said, hey, optimizers are super wrong in terms of cardinality estimation. This is like a problem you could look at. And there's sort of out of UChicago, same thing. And I was quite perplexed why there wasn't a lot of real-world systems that actually does this, despite a lot of academic research activities. And then Andy Pavlo from CMU published a paper earlier this year in CIDR, and the paper basically said, hey, in order to use ML for your real database systems, the bottleneck isn't actually in how do you design sophisticated models, how do you make their sort of one edge up. It doesn't matter if you're using GPT-4, you're using something simpler. As a matter of fact, you probably want simpler models if you're trying to make decisions real time. You can't afford for GPT-4 to generate whatever answers it needs to be. But the bottleneck shifted from model design to actually having access to real training data, which is the very key of building AI applications. And that is very, very difficult for academics to get access to. And industry systems tend not to be architected from the beginning to emit those data as needed for running the training. So we started a few years ago also at the same time thinking about this problem. And one of the first things we had to do is to re-architect our system to emit way more data so we can build machine learning models to learn on them. And just over the course of 4 years, we collected metrics from over billions of containers. We launched roughly about 20 million containers a day right now across all 3 clouds on the Databricks platform. So over 4 years, it's billions of containers, ran trillions of queries, and then also zettabytes of data. And through all this telemetry, we started building and looking at what are the possible optimization opportunities we can do using AI on our analytics system. And as I said earlier, one of the first things we had to do is to open up the engine, because data system engines were not really designed to emit the type of telemetry that's needed to do learning on. And this is not about just, hey, to tune a specific config parameter. This is about, for any heuristics, how do we just get rid of that heuristics in the design of the system and replace it with a real-time AI system. So we have to emit way more telemetry, treat it as sort of a real applied machine learning problem. And then this training evaluation that runs both online and offline. So online meaning inference runs on the critical path of the engine, so it needs to be super, super fast. And we also run sort of AI models that are more complicated, can run offline, and then use that to help correct the behavior. And all of this powers by our own platform running model serving. And I'll give you sort of just 4 examples of where we apply this sort of AI-driven optimizations. And the first is indexless indexes. It's very difficult to pronounce. And then liquid clustering, automatic data layout optimization, intelligent workload management. All right, let's start with indexless indexes. So we started the talk with index. What does indexes mean? If you think about what data warehouses, or I mean even honestly, databases ask you to do, OLTP databases, you do this all the time. You look at your queries to look at, hey, what tables and columns are accessed frequently and needs indexing, and you introduce index. Now, so in some sort of cloud data warehouses, they don't have the term called index, but they do have equivalent things, for example, optimization services. And now you start paying cost because of the right amplification of adding these indexes, and you're trying to maintain it. And then you go back, because sometimes you realize, hey, adding these indexes actually slow down my workload too much. Now I have to remove them and try to figure out what the other ones are, which I should be adding. It's a fairly complicated DBA grief loop. Again, just using our very simple example, select star from events, where user ID, a predicate on user ID. If you create an index, basically you can make, in most cases, make the system fast, and it's easy to think about because you just keep adding indexes for every sort of predicate you have. But it's no longer cheap because the system at some point becomes highly inefficient due to the right amplification. In some cases, you could come up with ways of maybe clustering or tuning your data set and your queries. So it's both fast and cheap based on the data layout, not necessarily just based on index. But then it becomes very difficult. It's sort of require a PhD level DBA to be doing that. Or you kind of just ignore maybe, hey, let me just have a table and do full table scan all the time. It's super, super slow, but it's not that difficult to maintain. All right. So the idea of indexes is, hey, what if you don't have to do any of this? Right? You don't have to create indexes. What if the system just learns using machine learning, so what your queries might look at, and then figure out how to run it efficiently. And it's just very fast. You don't have to do anything. Right? Now, sounds like magic. I'll tell you how. So we built this thing called Predictive I. It took us a very long time to come up with a name that would actually make sense. Anyway, Predictive I. And I'll show you the result first, and I'll explain to you how it worked. We basically were able to match, but I think this query's runtime are in seconds. And you might think, hey, 3.7 seconds is a very long time. This is actually an analytics query that runs across a super large data set. And we compared it with a cloud data warehouse that has the search optimization feature. And we turned on the search optimization feature for specific queries, which actually requires us to pay more in the benchmark. And then with what we call DB SQL, which is our data warehousing offering on Databricks, with Predictive I/O, it basically matched the performance of that. And we also do it for writes. It's just not for reads. But it just feels too good to be true. So how does that work? I've not shown this in public yet. This is the first time I actually showed it in public. The idea is very, very simple. Now, obviously, it's very complicated to implement, but it's very simple at a high level. So imagine this query in an analytics system, which is almost always columnar. There are effectively two ways of executing it. The first way is what we call, you would try to pipeline the fetch of all columns. So let's say we have 3 columns you're trying to read. One is just user ID, because you have to run the predicate filter on, and then you read the other 2 columns, A and B. One way is you do maximum pipelining. So you try to read all of them almost at the same time. Right? In this case, you might be actually reading unnecessary data, because if the filter is very selective, which is typically how people want indexes on, column A and column B might never be read until just a specific block that actually have a hit on the user ID 1 to 3. Right? So we're wasting work in this case. An alternative plan is you read the user ID column, which, because it's integer, tend to be highly compressed. So you can actually read it extremely fast, as if it's an index. And then you run the filter. And if the filter has any match, you go read column A and column B. All right? So when there's, in the former plan, if the filter has no match, we're wasting resources. In the latter plan, when there's no match, we don't have to read A and B. So we skip massive amount of I/O. Now, imagine, I show you a very tall example of 3 columns. Imagine in practice you have 20 columns, and because the predicate column tend to be highly compressible, you might be reading less than 1/100th of the data. But this sound like, okay, then why don't we just simply do this? Why doesn't every system do this? Just always read the filter column first and then read the rest if there's a match. Well, the reason is now if it's a not very selective predicate and you always have matches, doing the latter, you actually lose out on the opportunity for performance optimizations because you lose out on the pipelining. This requires a blocking operation to read the first column and then read the rest. So it will actually be strictly slower if the predicate is not very selective. So the art of all of this actually comes down to predicting whether there will be a match or not in a specific block of data. So that's what we built. We basically took in all the telemetry we've had in the past, and then and there's actually a basic live model in production. At the time of the scan for every single block, that model predicts how likely it is to have a hit on this block based on the predicates it's given. And depends on the likelihood, it applies a pipeline model or it applies a non-pipeline data fetch model. And this would result in some cases, a tens reduction in I/O, some cases like hundreds in reduction in I/O. Now the key is how well does that model work, and that's a lot of voodoo magic that basically looks at learning on the past. And honestly, nobody even understands exactly how it works once it's learned out, but empirically, it works incredibly well. It's so well that one day, we got a sort of Slack message. Sean is my CTO for DB SQL. He got a message from the solution architect, Usman. He said, hey, my customer asked if there's a bug with a new rollout of the system. One of their queries finished in just 2 seconds, which got 35 times faster compared with the old version. There must be a bug. So this is a very important customer. It's one of the largest customers at Databricks. We jumped on it, we analyzed it, we debug it, we're like, oh, it turned out the AI model now learned enough. And as a result, the query magically sped up. So the second example is Liquid. If you use analytics system, very likely you have actually done partitioning on data. It's a very effective thing to do, but it's also a very error-prone thing. Because, for example, in a very simple table that you have date and maybe customer, ID, partitions, just two-dimensional. You hit both problems. Sometimes you hit the problem of, hey, a specific partition might be too big because just I have a large customer on a specific day. And sometimes you hit, hey, specific partitions are too small because I have small customers partitioned across those dates. So the idea of Liquid is, in the cases that customers or users really have the domain knowledge to help speed up their workloads, we want to get that insight. But at the same time, we don't want a rigid partitioning structure that basically lets the user shoot themselves in the foot. So Liquid, when it sees, hey, there are a small amount of data based on kind of a query workload is learned, it will automatically coalesce across this column partition boundaries. And when you see, it doesn't have to go a specific way. It can even go into different dimensions, like for example, the date dimension, or you can actually combine 2 dimensions together to do the coalescing. The way it works is I think of this as, you can also do splitting. Hey, basically we'll actually split this dynamically. And the way it works is model this as a hyperplane, and then there's a data structure called KD tree that can basically balance out the leaves of the tree. And the trick, again, is when do you do that? So you can see kind of a theme of all of this AI optimization. Typically has to do with maybe kill algorithmic or system techniques. But the key is when do we apply that technique? Because that technique has trade-off. We're using machine learning model to predict how to minimize that trade-off. So when we introduce Liquid, we compare first with, we sort of come up with a very simple workloads that we see very common, which is you have continuous ingest coming to the system. And then we're just running queries on some columns. And when there's continuous ingest, the partitioning approach typically breaks down because a single batch of records may get scattered out into a lot of partitions. It's very expensive to write. And we have a new So another technique we released a while ago called Z-order, which was also quite problematic when it comes to continuous ingest. Liquid was able to accomplish both 2.5 times faster than our previous generation approach called Z-order, but more importantly, because Liquid is very, the KD tree property can be done in a very incremental way. Liquid, you always see a very smooth curve compared with a lot of other approaches. They're not very incremental, like Z-order. And then automatic data layout optimization. If you use sort of any data lakes, you probably struggle with, hey, I have to pick right file sizes, I have to think about clustering columns, and depending on your format using, you have to run optimize, vacuum, analyze, clustering. The choice of the file sizes are very important because it's workload dependent. But when you pick the right sizes, you can easily achieve some multiple orders, multiple magnitudes of improvements. So we rolled out this new thing called predictive optimization. It looks at the workload. So build a very simple actually AI model to predict when we should be doing, for example, compaction, when we should be setting the right file sizes. And we rolled it out in preview and so a few months ago. And every customer tried it, loved it. Even the ones that are most technical, because the ones that are most technical, while they can handle maybe manual tuning of their specific, like their own tables, but in any large company, they have probably hundreds of other sort of analysts or less technical user working against those systems, and they have no time to optimize those tables. Here's an actual histogram from Anchor that once they turned on the predictive optimization to do automatic data layout clustering, it actually shrunk down their storage cost by almost 2x because their storage costs were just super inefficient the way they were laid out by all these users. The last one is intelligent workload management. A very common thing you would see actually in cloud data warehouses is you define queues or priorities. You run queries across sort of different queues because for some queries you want to run in higher priority, some you want to run lower priority, and then or you spin up different sort of compute resources. You run queries against them. There's a very simple observation we kind of came up with, which is you don't, in almost all cases, you don't actually need to define priorities. What people really want is for fast query to run fast and slow queries to run slow. All right? What does that mean? It means if a query is supposed to run for a second, you better not wait. You should not let it wait in a queue because the difference between a second and the difference between 20 seconds is massive. But if a query is supposed to run for an hour, it's most likely offline. As long as it hits a certain SLA, it's okay. Nobody cares if it waits for half an hour in most cases because it's probably running overnight, right? So with that, now the job comes down to, okay, if we just simply don't ask customers for any priorities and ask them to send all queries into a single pool of resources for execution, how do we prioritize them? Well, then the key gets reduced into a machine learning model that predicts whether a query should be fast or slow, right? If it's fast, run it immediately. If it's slow, it's okay to queue it up. So we basically came up with this idea of let's build a machine learning model and let's learn from all the features we could find to predict how fast a query would be. And this is the intelligent workload management. Very simple idea. Now, of course, under the hood, there's a lot more work that gone into it. And when we rolled it out, we realized there's actually a 3x latency improvement overall across all the queries because there's actually way more short queries than long queries in most real-world workloads. So I give you quite a few examples. And I'm not claiming we solved this problem of database optimizations and eliminating trade-offs. But based on what we've seen and based on the sort of a few things we have done, we're pretty confident this is the right direction for the next decade to come. I don't think anybody will be able to come up with here's one thing that will rule them all. But what we can do is to look at every single heuristics that's ever introduced in all of the systems and ask ourselves, do we have to depend on heuristics? Or can we actually learn based on real-world telemetry and build machine learning models and build an actual, like treat it as an applied machine learning problem? And once we do that, we might finally be able to realize Codd's vision, all right, which is the users of large databases must be protected from having to know how the data is organized in the machine. And to maybe just broaden it again, just with my own interpretation. Database systems needs to be fast, easy, and cheap. And we can do that with AI. Thank you.